Hello everyone, my name is Ibrahim Yildirim. I am the second author of this paper. First author is Professor Ertuğrul Başar. I am pursuing PhD degree at Koç University in Istanbul and also working as teaching assistant at Istanbul Technical University. Today I will present our paper which has title as SimRIS Channel Simulator for Reconfigurable Intelligent Surface Empowered Communication Systems. Before start, let me briefly introduce the content of my presentation. First, I will give an introduction and motivation of our study. Then, I will present the RIS-Assisted Communication Systems and fundamentals of these systems. After that, I will introduce our channel modeling campaign for indoors and outdoors. Then I will show you a graphical user interface and user guide of the SimRIS Channel Simulator. After that, I will present our numerical and simulation results. Then I will conclude with final remarks. 6G wireless systems are expected to provide broadband and ubiquitous connectivity by supporting new use cases, including extreme capacity and very high mobility. And also it is expected to be integrated with satellite networks and autonomous systems. These attractive features can be supported by utilizing effective physical layer tools, such as ultra-massive multiple input, multiple output systems, millimeter wave and terrestrial communications, and reconfigurable intelligent surfaces. This is the most important one for our study. Here, the applications, trends, performance metrics, and the subtle technologies that will drive the 6G revolution are identified. In wireless transmission, the propagation medium is known as a randomly behaving entity between the transmitter and the receiver. It is degrading the quality of the received signal because there are uncontrollable interactions of the transmitted radio waves with the surrounding objects. But reconfigurable intelligent surface provides a new way to manipulate these interactions by optimizing the communication system performances. Reconfigurable intelligent surfaces are man-made surfaces of electromagnetic material, and it is electronically controlled with integrated electronics, and they have unique wireless communication capabilities. Reconfigurable intelligent surfaces are smart devices that control the propagation environment with the aim of improving the coverage and signal quality. This large number of small, low-cost, and passive elements on a RIS only reflect the incident signal with an adjustable phase shift without requiring a dedicated energy source for RF processing, decoding, encoding, or retransmission. Actually, this is a re-engineering the electromagnetic waves, and we can make a lot of manipulations on signal by using RIS, as you see here. In these days, RIS-empowered communication has received growing interest from the wireless research community due to its undeniable potential in extending coverage, enhancing the link capacity, mitigating interference, deep fading, and Doppler effects, and increasing the physical layer security. Against this background, there is an urgent need for a physical and widely applicable millimeter wave channel model to be used in various RIS-assisted systems in indoor and outdoor environments. In this paper, we aim to fill an important gap in the open literature by providing an accurate, open source, and widely applicable RIS channel model for millimeter wave frequencies. Before diving into the channel model and simulator, let me revisit the link power equation and the channel model of an RIS-assisted system without any obstacles or scattering objects between the terminals and the RIS. Then we will extend our model considering the existence of multiple interacting objects between transmitter and the RIS to model a more practical scenarios. Here, there is a pure line of sight links between the terminals. According to the Platt scattering theory, the transmitted signal is captured by each RIS element. Then scattered to the medium in all directions. Here, PN-RIS is the captured power by this element of RIS. Here, PT is transmitted power, GT is the gain of the transmitter, and GETX is the gain of the RIS element in the direction of transmitter. Lambda is wavelength. AN is the distance between transmitter and receiver. Transmitter and RIS. BN is the distance between RIS and receiver. This is the captured power by receiver by following this path. If you look at the radar range equation, there are similar equations in here. If we change radar cross-section parameters with this, we can obtain the same equations as you see. Due to the scattering nature of RIS elements, we can state that the total path gain is the product of the individual path attenuations of these two links. This is one of the fundamental properties of RIS-assisted communication systems. Here, for clarity of the presentation, PT is assumed 0 dB watt, and at the transmitter and receiver, the isotropic antennas are used. And we also assume that the gain of the RIS in all directions are equal each other. If we generalize the scattering concept given in previous slides for an RIS with n elements, here capital N represents the number of reflecting elements on RIS. The received baseband signal can be expressed as this. Here, alpha n denotes the controllable magnitude of RIS. Phi n represents the adjustable phase for each RIS elements. And if we consider the direct link between the transmitter and the receiver, we should add this term here. And PTR is the captured power by receiver for this direct link. Here we relax the system model of previous slides by assuming M scatterers between transmitter and the RIS as shown in here, while we assume a pure line of sight link between RIS and receiver. Here we should reorganize the captured power by receiver for each specific path, because we have 3 multiplication in here. Here, we can reorganize the received baseband signal through each possible paths by considering M interacting objects here. Here, let us re-express the baseband signal by separating the channel gains belonging to transmitter to RIS and RIS to receiver links. This is the path attenuation for RIS to receiver links. And we can re-obtain the received signal as in vector form, as you see. Here, G is the RIS to RX channel, H is the transmitter to RIS channel, and Phi is the RIS phase shift matrix. Before concluding this section, we note that this baseband signal can be used to model the power budget of an RIS system operating in a more realistic environment with multiple scatterers. However, this model again does not capture the variations of the environmental objects and transmitter-receiver movements. In the scope of this work, the unified narrowband channel model for RIS-assisted systems in indoor and outdoor environments is presented for the first time. Here we consider the 5G mmWave 3D channel model with random number of clusters and scatterers. This model includes many physical characteristics such as loss probability, shadowing effects, shared clusters, realistic gains, and array responses. Here, we consider that the transmitter lies on the YZ plane, while the RIS lies either on the XZ plane for scenario 1 or YZ plane for scenario 2. This geometry for indoor office environment, but we can extend to outdoor environments by modifying the certain system parameters. In this model, we assume that the existing interacting objects or scatterers are grouped under C clusters, and each clusters have SC subarrays, as you see. Therefore, transmitter to RIS channel coefficient H can be written for a clustered channel model by considering array responses and path attenuations. Here, beta is the complex path gain, L is the path attenuation, and H loss is the loss component of this channel, and A is the array response. For detailed calculation of array response and other details, you can check our complementary work from here. For the attenuation of the transmission paths, we adopt the 5G path loss model, which is applicable to various environments, including urban macro, cellular, and indoor hotspot. And number of clusters C can be modeled with Poisson distribution. And number of subarrays for each clusters can be modeled with uniform distribution in here. And also azimuth and elevation departure angles follows conditional Laplacian distribution. And to ensure that at least one cluster exists in the environment, we consider this equation. The fundamental difficulty in modeling of a wireless channel involving an reconfigurable intelligent surface is that C clusters, as well as their subarrays, are randomly generated. And the azimuth and elevation arrival angles for an RIS cannot be modeled random as in 3G PP-LTE and 5G spatial channel models due to random orientation of mobile receivers. As we said before, we can easily adopt the 5G path loss models, and we can easily configure this path loss model depends on the indoor or outdoor environment by using these parameters. Another important points for channel modeling are loss component and loss probability. Here, IH is a Bernoulli random variable taking values between 0 and 1 and characterizes the existence of a line of sight link for a transmitter to RIS link. Here, DT-RIS represents the transmitter to RIS separation. These are reported based on intensive measurements in various indoor office environments, and we can say that line of sight probability decays very fast with increasing distance. As we observe from our analysis, if we look at the RIS cases, if RIS is positioned higher than the transmitter in z-axis, the loss probability for RIS case is equal to 1 regardless of the distance. For the calculation of line of sight dominated RIS to RX channel G in an indoor, we should recalculate the RIS array response in the direction of receiver. Finally, the vector of these line of sight dominated channel can be generated as this. Furthermore, for indoor, using single input, single output millimeter wave channel modeling, the channel between these two terminals, I mean transmitter to receiver terminal, we can easily obtain the channel by this formula. Here we assume share cluster assumption between transmitter to receiver and transmitter to RIS link, since the distance between RIS and receiver is smaller than correlation distance. For outdoor channel modeling, the major change will be in the channel between the RIS and the receiver. For this channel, we should consider a small scale fading as well with a random number of a unique cluster here. And for this case, we can easily obtain these three channel coefficients by following the similar methods as in indoor environment. Furthermore, another important point here is that we assume that RIS and the receiver are not too close to ensure that they have independent clusters. In this part, we introduce the open source and MATLAB-based SimRIS Channel Simulator, which can be used in channel modeling of RIS-assisted systems with tunable operating frequency, terminal locations, number of RIS elements, and environments. The graphical user interface of our SimRIS Channel Simulator is given here. As you see, environment, RIS position, and frequency is user selectable parameters. User can select these parameters, and user can also enter the number of RIS elements and number of channel realizations from here. For locations, you can use recommendation button and you can easily obtain the true location value depends on environment, RIS position, and frequency. By using SimRIS Channel Simulator, we obtain a achievable rate comparison for the communication system with and without RIS in an indoor environment. These are the simulation parameters for this comparison. As we take a look, this figure and this figure for scenario 1 and this figure for scenario 2 for an indoor environment. If we increase the location of the RIS in z-axis, we will obtain significant improvement in achievable rate performances for both scenario 1 and scenario 2. Another important parameter is number of reflecting elements in here. If we increase the number of reflecting elements, we will obtain again significant gain on achievable rate performances. And therefore, we can say that RIS can be used as an effective tool to boost the achievable rate in indoor environments when both the transmitter to RIS and RIS to RX links are line of sight dominated, because increasing the Z-RIS value will provide higher line of sight probability. These figures provides the effect of varying RX positions through X and Y axis on the achievable rate. In A, there is direct link between the transmitter and the receiver, but in figure B, there is no direct link between transmitter and the receiver. And these are the simulation parameters for this comparison. And we are in outdoor environment and at 28 GHz frequency. These are the positions for each terminal. From figure A, we observe that the highest achievable rate is obtained when the receiver is close to the transmitter, because the channel between the transmitter and the receiver is more dominant than RIS-assisted link in terms of achievable rate. Furthermore, if the receiver moves to an area far from the RIS on the X and Y axis, the effect of the RIS will drastically diminish, as shown in figure B. We observe that the most decisive performance parameter is the separation between the RIS to RX link when the direct link is blocked between the transmitter and receiver. This paper has been a first step towards physical channel modeling for emerging RIS-empowered networks. And our SimRIS Channel Simulator can be used effectively in channel modeling of RIS-based systems with optional operating frequency, terminal locations, number of RIS elements, and environments. The fundamental aim of this study is to pave the way for an accurate channel model which is compatible with real-world experiments. And MIMO extension of our SimRIS Channel Simulator is available. You can access by using this link from our website. Thank you for